record just in case somebody wasn't here and they'd like to watch your guys' questions and answers before we go on. So, bit of a news update. The citrus class is available. You may have gotten an invitation to it. Don't bother joining it. They have done that so wrong. We're going to stay here on this website, so everything will just stay here. You don't have to go to Citrus at all. Don't worry about it. And then the next class, next semester, is on here as well. So you may have gotten the invitation for that today for the second semester course. You can join that if you want. I'll start putting stuff up there too, which just means I can propagate both Unit 3 and 4 with assignments and resources and all that kind of stuff. So everything can be up. So yeah, so there's the piece of news. Don't have to worry about any of the citrus stuff. You can ignore it. So yeah, I think I put everything up grades wise as far as quizzes go over the weekend. So it's just the other exam today. Exam today has 45 questions instead of 30 because it's 3 chapters instead of 2. Basically did like 15 questions a chapter, the idea. So yeah, questions before you take the exam or questions you just have. You can either type in the chat or you can do a hand raise, or you can unmute yourself. However you want to do it. I'll just draw this cat until you think of a question. Or how about a dog? No? No questions? Can you break down the whole isotope bit for me? Just a basic run through to make sure it's all right. So Dalton thought that atoms were balls. Dalton thought that atoms were balls. They were the smallest thing. That's why he called them the atom, because it meant like you couldn't cut it anymore. Beverly Hills. And that meant you couldn't cut it anymore. So when we figured out that there was positive and negative stuff in there, they just assumed that all the positive stuff was the same. It was the stuff that had all the mass. Well, when they later started understanding the nucleus more, they found out that there was protons and neutrons. So in the case of hydrogen normally is 1 proton and then 1 electron. But you'll notice that if there's a neutron down here, there's 1 electron and there's 1 proton. So this is hydrogen. This is what we call hydrogen 1. But this is also hydrogen. It's hydrogen 2. And these are isotopes. Basically, it's just every single element the number of neutrons varies. The point of the neutrons in the nucleus is to stabilize the positive charge, because the positive charges are trying to push on each other. So the neutrons in there are kind of holding them together. And then there's another isotope of hydrogen called tritium, which has 1 proton and 2 neutrons in it, and then still 1 electron out here. So this would be hydrogen 3, called tritium. So all these 3 are isotopes. But when it comes to the average atomic mass, if you look at Earth, there'll be 9,998 of these in a 10,000 hydrogen sample. There'll be 1.5 of these, and there'll be 0.5 of these in a 10,000 thing sample. So when we go to do the math on what the average atomic mass is, we do 1 and then times the 9,998, and then we do 2 times 1.5, and then we do 3 times 0.5, and we add all those together. That's where the average atomic mass comes from. Now, to get the accurate numbers that you see on the periodic table, they don't use the 1, the 2, and the 3. They use the actual, instead of AMU, they use the actual gram numbers and then convert it to AMU. So that's where you're getting some of these fractions. Because an AMU is based off of carbon. To get the actual like baseline, like what is 1 proton's mass, they used carbon-12. Because carbon-12 has 6 protons and 6 neutrons. So if you take 1/12 of a carbon atom, then you can figure out what the mass of a proton is. And that's what the AMU is based off of. So that is isotopes and average atomic mass in a nutshell. Some elements on the periodic table look like they have average atomic masses that are basically whole numbers. And, a good example of this is hydrogen with its 1.001. And that's because, hydrogen 1 is the most abundant hydrogen in the universe by far. There is hydrogen 2 and there is hydrogen 3, but they're so low that that's where this little 0.1 comes in. It's kind of adding to the mass. But then you have stuff like chlorine. Chlorine has an average atomic mass of 35.456. And that's because chlorine, the isotopes of chlorine are actually 37 and 34 and 36. So those are the major ones. And so it's kind of split between some of them. It's all over the place. And that's where that average comes in. And then there is the elements on the periodic table like plutonium. Plutonium will just have a bracket and it'll say 244 and it won't have any decimals. And that's because remember that the average atomic mass that's found on the periodic table is based off of the percent abundance it is on the planet. Well, plutonium doesn't exist on the planet. It is man-made. So 244 is just the longest lived isotope, meaning the one that doesn't fall apart. So that's why it sits there. That's why it doesn't have decimals. All right. So the next question said, could you explain the trend in ionization energy and how it increases and decreases across the periodic table? So here's our little periodic table, boop, boop, and then we have right down here, and we have right there. The F block is right here, but I'm not going to draw it because it's not that entertaining for ionization energy. So remember, the definition of ionization energy is the energy it takes to remove an electron. The way we do that is we take our little nucleus here, and we have a bunch of shells of electrons in there, and the outer shell, we're going to shoot an X-ray at it. X-rays have enough energy to kick electrons out of atoms. That's why they're called ionizing radiation. And so what we do is we shoot an X-ray at it. And as you guys know from this chapter, we can use the E equals energy H nu. So we can figure out the energy of the X-ray, and that'll tell us the amount of energy it took to remove this electron. So if we look over here, we have the noble gases, and there's helium, and then neon, and krypton, no, argon, and then krypton, and then xenon, and then there's oxygen. But basically, these guys have full energy levels. They have full valence electrons, and so that makes them very happy. So all of these elements here, these guys who have 7 valence electrons, 6, 5, 4, 3, 2, and 1, these guys, this have 8 valence electrons. They all are going to, these guys right here, are all going to want to gain electrons. And these guys over here are all going to want to lose electrons. So these guys all want to form positive ions, and these guys want to form negative ions. So if these guys want to form negative ions, then the amount of energy that you're going to need to get them to lose an electron is going to be huge, because they don't want to lose, they want to gain. So it's like if you had, $900 and you needed $1,000 to buy something. Well, you're not going to want to spend any money. You're going to kind of keep saving. And so even if you see something cool, you're going to be like, no, I want to save. Whereas in all these guys over here, they want to lose their electrons to get to 8. These guys over here that are 1, 2, and 3. 4 is kind of in the middle. It kind of does what it kind of doesn't do this as often. Except for if you're down here into the, the tins and the leads of the world. That's why that staircase exists, kind of is the cut between this gain and losing thing. So ionization energy then is going to be extremely high as we go up and to the right. So the lowest ionization energy element is going to be down here, francium and cesium. And then what's next to francium? Radon. And then I think it's barium. These guys are our lowest ionization energy. So this is low. And then obviously helium with its 2 electrons is going to be the highest. This is our highest. And the reason why this is so high at helium and less high at xenon and all those guys is because of what's called effective nuclear charge. If we look at the nucleus of a helium atom, those 2 electrons are basically right there next to the nucleus. They're feeling all of the effects of the nucleus. But if we look at xenon, for instance, the outside electrons are, because xenon is in row 5, there's 1, 2, 3, 4, 5 energy levels here. And that's where the electrons are. So that positive charge in the center is getting shielded by the other electrons in here. And so it's a little bit easier to steal this electron. My analogy I give my students in class is, imagine you are a dairy farmer. If you only have 1 cow, you know where that cow is all the time. But if you have 10,000 cows, then somebody could roll up one day, steal your cow, and it would take you a little while to notice. And that's kind of what's happening with the decrease in ionization energy as you go down the group. The increase in ionization energy as you go across is this whole effective nuclear charge. Effective nuclear charge increases as we go from left to right. That's ionization energy. So basically, if you're asked on a test who has more ionization energy, and they say like fluorine, and they say, copper, well, there's copper down there, and there's fluorine, so fluorine's higher. All right. Can you explain how to fill out and use an Aufbau diagram to find the electron configuration? So Aufbau diagram is an energy diagram where you have the orbits, and the little box there is how many orientation each one of those orbits have. The 1 here is our principal quantum number. Our S is our shape, and the box is our orientation. Well, S only has 1 shape. Then, because this is an energy diagram, the next electrons require more energy to exist in that higher shell. But this is the second shell, so it contains two shapes. And the S, while it only has one orientation, the P has three. The third energy level has an S, and it also has a P. It should have a D, but because of electron shielding, the D doesn't show up until the fourth energy level for some reason, because of the electron shielding. And that has 5 orientations, so there's 5 lines, and then we have 4p here. So the game is basically Connect 4. The Aufbau principle is basically gravity. If you were thinking this game like a Connect 4 game, and you dropped the checker would go, there's no checkers in this board, so the checker would just go all the way down to the bottom. And that's what the Aufbau principle states. So if we have hydrogen and we use its one electron is going to go all the way to the bottom to what we call the ground state, so the lowest amount of energy required to be that atom. And so because we only have one electron for hydrogen, we only draw one little arrow, and so that gives us the electron configuration of 1s1. If we do helium, the Aufbau principle says it needs to go all the way down to the lowest energy, so we'll get this one here. Then the Pauli exclusion principle kicks in. The Pauli exclusion principle says that no two atoms can have the same 4 principal quantum numbers. And what that means is we have to introduce the idea of the fourth quantum number, which is spin. And that's why we draw the arrows up and down. But when it comes to the electron configuration, you just leave spin out because it's assumed that they're opposite spins. So that's the Pauli exclusion principle. It just means use up and down arrows. When we get to lithium and beryllium, we just keep adding electrons. So 1s2, 2s1, and then beryllium. is 1s2, 2s2. That all makes sense. When we get to boron, we go 1s2, 2s2, and then we have 2p1. The next atom, carbon, is the first time you're going to get what's called Hund's rule. And Hund's rule is basically when you go to put that 6th electron in here, you don't put it next to this one, you give it its own box. And while this doesn't show up in the actual electron configuration, this is what gives you what's called unpaired electrons. So carbon here has our 2 unpaired electrons because it has empty seats that require the same amount of energy as they do to be in any of those orientations as it does to be next to it. It's a little bit easier for it to be over here than it is to be here because it doesn't have to worry about opposite spin. It can go whatever direction it wants. We have nitrogen, where we get a 3rd unpaired electron. But again, in the electron configuration, it doesn't matter. And then finally, now we can go to oxygen, which has 8 electrons total. But now we're starting to pair them up again. And then we have fluorine, 1s2, 2s2, 2p5. And then finally we have neon, 1s2, 2p6. So that's how you use that. And that's what those principles are. But if you don't want to remember them as the Aufbau principle, you can just think of it as the lowest, go to the bottom first, draw an up and down arrow, and if you have empty seats, fill them up first before you put the arrows in. I didn't ask any of those Hund's rule or Pauli exclusion principle rules on the test because when it came down to it, I was really just more interested in you being able to either write this or see this and recognize that it's this. So I know the book and stuff has like a drawing and says like, well, what's wrong here? Which one's right? And the answer is it doesn't matter for the test. There are also exceptions to the rules. For instance, if we go when we talk about energy, if we start getting into the D block, because of that energy difference between being D and 4s, 3D and 4s are very similar to each other, is that sometimes, like in the case of this, it's like, what's the correct electron configuration? Well, in reality, it actually does this, and then this guy over here empties out, and then we get partially filled. And again, that's exceptions to the rule that you can learn if you want to do, inorganic chemistry when you go to college. So, and remember, if you're on the internet and you're looking up electron configurations, they will write them backwards. So you want to make sure you're not doing that. You want to use the order. The reason for this is that modern electron configurations, like say noble gas configurations, say for instance we have like barium here. This is barium with its xenon 6s2. But if we go to the very next one on the periodic table, lanthanum, if you looked up lanthanum, it'll say xenon on the internet, it'll say xenon 4f1 6s2. And that's backwards because of the way that it's written. This is because these are the electrons that are called the valence electrons. And so they've just, in the past 10, 15 years, they switched to this. But yeah, don't use the internet electron configurations. So next, what else you got? Ollie? You guys good? So another heads up on the test, you had two equations for this test. I didn't ask you to do any math. I just wanted you to know what these were. I was more interested in the electromagnetic spectrum. So like if we're talking about the electromagnetic spectrum where we have gamma over here and we have radio over here, and the question is like, who is more energy? Is it gamma or is it radio? Who is the shorter frequency? Is it radio or is it gamma? Who has the longer wavelength? Is it gamma or is it radio? Visible light's kind of right there. Then we have X-rays. Sorry, ultraviolet, X-rays. We have infrared and microwaves. So know the electromagnetic spectrum. There's only a couple questions on that. But I didn't have you do math. I know in the practice problems, they're like, okay, well, if the energy is like 1.6 times 10 to the negative 17th joules, then what is the wavelength? Nah, you don't have to do that on the test. They have moved, in the standards, they have moved that all to physics. So preguntas. Okay, then. I'm available during the day if you want to shoot me an email. either to the R. Sullivan at Glendora, or if you want to just do it in the Canvas, I'll have my Canvas open and I'll see your stuff pop up in the inbox. So you can take the test all day long, and that's your attendance for today. So once you're done with the test, you're done with today. And throughout the day, I'll start putting in the stuff for Unit 3 and 4, since I know they're not going to close this class. And then I'll your grade is automatic. So your grades are on Canvas, and they should be visible. Let me see. So if we go to Canvas, if I click on grades, everything should be automatic and visible to you. Yeah, it's not hiding anything to you right now. So on Canvas, there's a little thing that says grades, and you click on that and it will show you your grades. Here, I'll show you the student view. So if I go to home, student view. So now it's calling me a student. And as you can see, there's this little box grades right here. So if you click on that, it'll show you your grades. I don't have any grades because, you know, I'm not a student. So that'll show that. There you go. Any other questions? All right, everybody. That's it for today. Again, if you have any questions, just let me know.